Discussing about the mutual inductance. Mutual means between the two. So here we have got two different coils. So the concept of mutual inductance defines that when two coils are in close proximity, if the current changes in the one coil, that change in current is opposed by a back EMF that is produced in the second coil. To verify that, we have got two coils. One is connected to a battery and a key, and another coil is connected to a galvanometer. That means here we are having no energy source. So what we have done, when we press the key on, the current increases. So during that increase in current, here the flux is produced. How the flux is produced? The flux is produced, and by that change in flux, here the current is produced in this coil, by which we get a deflection. Now, when the key is pressed off, so the current decreases. So when the current decreases, the flux linked with this coil changes. So again, here the current is induced in this coil, by which the galvanometer gets deflection. But the deflection is different or opposite when we press on and when we press off. So from here, we verify that when two coils are in close proximity, if in one coil the current changes, that current change produces a flux that is linked with the another coil, and by that flux linked with that coil, there is a current produced, or there is the induced current produced, which opposes the change in current in this coil. So we have got two coils in close proximity. So this inductance is called as mutual inductance. So here we have that phi 2, the flux produced in the second coil, is directly proportional to the current passing through this coil number 1, that is I1. Here, to eliminate this proportionality, we have to introduce constant of proportionality, and that constant of proportionality is coefficient of mutual inductance, that is M. Now, we also have that if back EMF is produced in this coil, that back EMF is directly proportional to the rate of change of current in this coil. So current change in this coil leads to the production of back EMF in this coil, as these coils are different. So we have got the name mutual inductance. In self-inductance, as already discussed, there is only one coil, and in that coil, a back EMF is produced that opposes the change in current in that coil. Here the case is different. Here in the second coil, the EMF is produced, that back EMF produced opposes the change in current in coil number 1. So the name of mutual inductance. Now we have that if E2 is the EMF produced in the second coil, that is directly proportional to the rate of change of current in first coil, di1 by dt. So E2 is, eliminating this constant of proportionality, introducing constant of proportionality, that is coefficient of mutual inductance, so di by dt. As it opposes, so we have to introduce a negative sign, m di divided by dt, where m is the coefficient of mutual inductance. Now we would like to define the mutual inductance. From this, phi 2 is equal to mi1. If I1 is equal to 1 ampere, in that case phi 2 is equal to m. So we will define the mutual inductance as numerically equal to the flux that is linked with the coil number 2 when the current passing in the coil number 1 is equal to 1 ampere. Now from this equation, E2 is equal to m di1 by dt. Dropping this negative sign, as this negative sign depicts that the EMF produced opposes the change in current in this. Having the magnitudes only, E2 is equal to m di1 by dt. Now, if the rate of change of current di1 by dt in the first coil is equal to 1 unit, in that case E2 is equal to m. So we can define the coefficient of mutual inductance as the EMF produced in the coil number 2 when the rate of change of current in the coil number 1 is 1 unit. Now talking of the units and dimensions, we have that m is equal to phi divided by I, phi 2 divided by I1. We have that the units of phi are Weber and the units of current are ampere. So the units of mutual inductance are Weber per ampere, and this Weber per ampere is called as Henry. So the SI unit of mutual inductance is Weber per ampere or Henry. Now from this equation, E is equal to m di by dt. So coefficient of mutual inductance is E di by dt. Now the units of EMF are volts, current are ampere, and time are seconds. So the SI units are volt second per ampere, and that volt second per ampere is called as Henry also. So the SI units are Henry, that is equal to Weber per ampere or volt second per ampere. Dimensions of M. From the units of M, M has got the units of volt second per ampere, and we know that the voltage is work done per unit charge, that has got the units of ml2 t minus 2 divided by charge has got at. Now second has got the dimensions of time and ampere has got the dimensions of a. So we have here t and t goes, so we are left with ml2 t minus 2 divided by a raised power 2. This a2 goes to the numerator and becomes a minus 2. So we have ml2 t minus 2 a raised power minus 2. These are the dimensions of the mutual inductance. Now, the coefficient of mutual inductance depends upon the geometry of the coils, that is, size of the coils, shape of the coils, number of turns of the coils, and nature of the core. Nature of the core is material on which this coil is bound. It can be air, it can be soft iron. So, the coefficient of mutual inductance depends upon that also. Number 2, it depends upon the orientation of the coils. Orientation of coils, that is, how far or in which direction these two coils are held. Let us discuss about the coefficient of coupling. Coefficient of coupling. The coefficient of coupling is called as K. Now, the coefficient of coupling is defined as, or the coefficient of coupling gives us the amount of coupling of the magnetic flux produced by the one coil with another coil. K is equal to root of m, that is the coefficient of mutual inductance divided by L1, L2. L1 is the coefficient of self-inductance of one coil and L2 is the coefficient of self-inductance of two coils. If the coils are bound in this direction, like this, the coefficient of coil K here is maximum. If the coils are held in this direction, the K is in between. And if the coils are held in this direction, this is coil number 1, this is coil number 2, K is minimum. So the coefficient of coupling is maximum. Here the coefficient of coupling is in between this case and this case. Here the coefficient of coupling is minimum. That means in this orientation, minimum amount of flux that is produced by the change in current in this coil 1 is linked with 2. Here, some of the flux that is produced by this is lost, so not that much of flux is linked with this coil. Here, all the flux produced by coil number 1 is linked with the coil number 2. So in this case, the coefficient of the coupling is, or K, is maximum. Thank you.